Welcome to a journey through the mesmerizing patterns of nature. From the grandeur of landscape to a minute details of a leaf, nature's designs are both intricate and profound. These patterns are not random but reflect an underlying order that shapes our world.
Nature is a master artist, creating patterns that captivate our senses and inspire wonder. From the microscopic to the majestic, these patterns reveal the hidden order of the natural world. Nature is a canvas of incredible complexity and beauty, where certain shapes and patterns repeat across different scales and forms. Today, we'll explore 12 fundamental shapes and patterns that are woven into the fabric of the natural world.
The symmetry often refers to a property where a shape or equation remains invariant under certain transformations, such as rotations, reflections, or translations. For example, a circle is symmetric around its center because it's rotating it by any angle doesn't change its appearance. Symmetry is prevalent in nature, from the bilateral symmetry of butterfly wings to the radial symmetry of starfish. This balance enhances functionality and aesthetics.
Symmetry is a common theme, found in butterflies and flowers. The bilateral symmetry of a butterfly's wings and the radial symmetry of a daisy ensure balance and beauty. Yet, asymmetry also plays a role, adding uniqueness to each individual in a species.
A spiral is a curve that originates from a central point of progressively moves away while revolving around the point in a circular or curved path. Spirals can be found in both natural and mathematical contexts, and they have vary in complexity. Examples of spirals: shells. Many shells such as those of Nautilus exhibit a logarithmic spiral. Galaxies. Spiral galaxies like the Milky Way have the extended outward in a spiral pattern. Plants. The arrangement of leaves or seeds in certain plants such as sunflowers and pine cones often follows a spiral pattern.
The Nautilus shell follows the same spiral, providing an efficient way to grow without changing shape.
Cracks is often formed in ways that reveals underlying patterns. These patterns emerge to material properties and the force applied to it. Cracks tend to follow specific paths or create specific shapes, which can be remarkable and consistent, and are often mathematically describable. Example of cracks: mudflats and coal stalls. Areas often show this polygonal cracks pattern during the low tide. As the mud dries out, it forms a network and interconnected cracks, displaying a natural hexagonal patterns. When the ice forms underwater bodies, it can be cracked due to the thermal expansions or contract. The crack is ice often follow straight line to create a geometric patterns.
Understanding crack patterns helps to predict how materials will behave under stress, which is crucial for designing durable structures and understanding geological processes. These cracks can form intricate patterns.
Fractures. Fractures occur in various patterns due to the way materials respond to stress or strain. An example of fractures is columnar jointing. This geological formation features thousands of interlocking basalt columns, mostly hexagonal, formed by the cooling contraction of lava. The regular patterns result from the even cooling of the lava as it solidified.
Imagine standing before the Giant's Causeway in Northern Ireland, where nature has etched its masterpiece onto the Earth's surface. Thousands of basalt columns, primarily hexagonal, rise in geometric precision from the shoreline. These columns are not just random formations. They are the result of ancient volcanic activity. As lava cooled and solidified, it contracted in such a way that it fractured into nearly perfect polygons, each one a testament to nature's penchant for symmetry.
Waves in nature reveal the dynamic processes shaping our world, from the grand scale of ocean swells to the minute ripples in sand. These patterns demonstrate the influence of various forces including wind, gravity, and biological activity, creating a diverse array of wave phenomena across different environments. Each example provides a unique glimpse into the rhythm and flow inherent in natural systems. Example of wave. The waves at Pipeline, Hawaii. The pipeline surf break on Oahu's north shore is famous for its powerful barreling waves. These ocean waves are shaped by the interaction between swell and the underwater reef, creating dramatic and consistent wave patterns ideal for surfing.
These examples showcase the diverse ways in which wave patterns manifest across various natural environments, illustrating the influence of physical forces on the formation of these intriguing patterns.
Bubbles. Bubbles in nature exhibit fascinating patterns and behaviors that can be observed in various contexts. They are created when a thin film of liquid traps air or gas, resulting in a spherical shape due to surface tension. Examples of bubbles. Soap bubbles on a rainy day. Soap bubbles can form when raindrops mix with substances like decomposing plant matter or soap residues. These iridescent and colorful patterns of these bubbles result from a light interference with a thin film of soap. On a rainy day, in a forest or meadow, you might observe these transient, colorful bubbles drifting through the air.
These highlights how bubbles interact with natural processes to create diverse and visually captivating patterns. Whether through biological activities, environmental conditions, or physical phenomena, bubbles in nature offer a window into the intricate and beautiful patterns that can arise in the natural world.
Foam. Foam is an intriguing phenomenon that occurs when a gas is dispersed in a liquid or solid matrix. Form bubbles that create a fruity texture. This can happen in a various environment and contexts, resulting in a wide range of natural patterns. Examples of foam. Ocean foam, also known as a sea foam, forms when a sea water is agitated by winds or waves. The mechanical action introduces air into the water, causing bubbles to form and create a frothy. Bubbles layer on the surface. Sea foam often appears in a patchy, fruity layer on the shorelines with patterns that can vary based on the wind directions, wave activity, and water salinity. It can create intricate organic shapes as it interacts with the currents and the waves.
Foam in nature reflects a dynamic interplay between gases, liquids, and solids, resulting in a variety of fascinating and diverse patterns. These natural foams can be temporary or persistent, depending on the environmental conditions and the processes involved in their formation.
We have tessellation. Tessellation in nature refers to the pattern created when shapes are arranged in a repeated, interlocking manner, without gaps or overlaps. This geometric concept, which originates from mathematics and art, appears throughout the natural world in a variety of forms and scales.
Example of tessellations. Honeycombs, created by bees, are one of the most well-known natural tessellations. The hexagonal cells in a honeycomb are arranged to maximize space and efficiency. The hexagonal tessellation of honeycombs is highly efficient for storing honey and pollen, as well as providing a structure for the development of larvae. The pattern is both functional and aesthetically pleasing, reflecting the optical package of hexagonal shapes.
Next, we have animal scales and shells. The scales of certain reptiles and the shells of various mollusks exhibit tessellation patterns. These structures are often hexagonal or other geometric shapes that fit together without gaps. In animal scales,
such as those pangolins or reptiles, tessellation helps in creating a protective armor that efficiently cover the animal's body. Similarly, the shells of mollusks like clams and snails can exhibit tessellated patterns.
Tessellation involves repeating shapes without gaps or overlaps. Honeycombs and animal scales and shells are excellent examples, showcasing how tessellation maximizes space and structural integrity.
Meander. Meander refers to a winding sinuous path taken by rivers, streams, or other natural features as they flow through their environments. This pattern is characterized by a series of broad, looping bends that create a serpentine route across the landscape. The meandering pattern is not only visually striking but also plays a crucial role in shaping and influencing the surrounding environment.
Examples of meander. The River Thames in UK. The River Thames meanders through the southern England, creating a series of broad loops and bends. The meandering pattern of the Thames is evident in its historical and temporary maps, illustrating how the river has shaped the landscape over time. Next, we have the Amazon River. Features extensive meandering patterns across its vast floodplain. These meanders contribute to the formation of oxbow lakes and wetlands, which are crucial for the region's biodiversity.
Meandering is a natural pattern characterized by winding, looping paths formed by the processes of erosion and deposition in rivers, streams, and other fluid systems.
Fractals are intricate patterns that repeat themselves at various scales, exhibiting self-similarities across different levels of magnifications, and in nature's fractals are prevalent in the organizations and structures of various natural phenomena. These patterns, characterized by these complex repeating shades and structures that similar regardless of the scale at which they can observe.
Examples of fractals. Trees. The branching patterns of trees are a classic example of fractals in nature. Each branch of a tree divides into smaller branches, and those smaller branches further divide, creating a self-similar structure. The branching pattern of trees, including the arrangement of leaves and the distribution of branches, resembles a fractal structure. This pattern is efficient for light capture and nutrient distribution. Snowflakes exhibit fractal patterns due to the way water molecules arrange themselves as they freeze. Each snowflake has a unique, intricate pattern that is self-similar across different scales. The six-fold symmetry of snowflakes and the repeating patterns of their crystalline structure reflect fractal geometry. Cauliflower and Romanesco exhibit fractal patterns in their arrangement of florets. Each floret is a miniature version of the entire vegetable structure. The repeating self-similar structure of florets in Romanesco mirrors the fractal nature of the whole vegetable. The spiral arrangement of Romanesco florets demonstrates fractal geometry, with each spiral mimicking the larger structure.
Fractals in nature demonstrate the beauty and complexity of self-similar patterns that repeat across different scales. From the branching of trees to the structure of snowflakes and the layout of river systems, fractals reveal how simple rules and processes can lead to complex and intricate natural designs. These patterns not only enhance the aesthetic appeal of natural phenomena but also play functional roles in optimizing processes like nutrient transport, energy capture, and habitat formation.
Stripes. In stripes, nature refers to repetitive, linear patterns characterized by alternating colors or textures that run parallel to each other. These stripes patterns can be observed across various natural phenomena and serve different functions, from camouflage to attracting mates.
Examples of stripes. Zebras. Zebras have distinctive black and white stripes that help blend into the grasslands and confuse predator or insects. Tigers. have unique stripe pattern that help individuals recognize each other, and pattern can vary amongst subspecies.
Stripes are diverse and serve multiple functions, from camouflage and communication to thermoregulation and aesthetics. They appear across various organisms and environments, creating patterns that are both functional and visually striking.
Spots. Spots in nature refer to distinctive, round or irregularly shaped marks or patches of colorful or texture that contrast with their surroundings. These patterns are often characterized by their localized, disparate appearance, creating a scattered or irregular distribution across a surface.
Examples of spots. Leopard spots have distinctive rosettes, spot patterns on their fur that help them blend into the dappled light of their forest or savanna habitats. Fly agaric mushroom. It has distinctive white spots on its red cap which can attract insects and aid in spore dispersal.
Spots in nature represent a fascinating aspect of pattern formation, characterized by localized, contrasting marks or patches. These patterns play diverse roles, including camouflage, warning signals, mating displays, and thermoregulation. From the striking spots on a leopard's coat to the subtle patterns on a mushroom, spots provide critical functions that enhance survival, reproduction, and interaction with the environment.